There is a kind of road that general relativity permits, but no traveller has ever found. It leads nowhere new. You could follow it forever, moving slower than light the entire way, never breaking a single law of physics, and arrive exactly where you began. Not in the same place, in the same moment. Your own past waiting for you, with you already in it. Einstein's own equations allow this. They have allowed it since 1949, when a quiet logician walked into the Institute for Advanced Study and handed Albert Einstein a birthday gift. A solution describing a universe that rotates and inside which every point in space and time lies on a loop back to its own history. Not a metaphor, a geometry, a worldline that closes on itself like a ring. Physicists call these closed timelike curves. The popular imagination calls them time machines. But the closer you look, the stranger the truth becomes. These loops are not doorways. They are dead ends, cul-de-sacs cut into space-time, paths that go somewhere only to return you to your starting point, and on which, by the mathematics itself, nothing new can ever happen. By the end of this exploration, you will understand what a closed time-like curve truly is, how it emerges from rotating universes, spinning cylinders, and the throats of wormholes. Why a block universe makes such loops harmless rather than paradoxical. What Stephen Hawking proposed to forbid them, and why he could never prove it. And what these sterile loops quietly reveal about cause, information, and why anything exists at all. If you find value in explorations like this, consider subscribing, which helps these deep dives reach more curious minds. Now, let us begin. Begin with the road itself, because the whole story lives in its geometry. In ordinary life, time feels like a current that carries everything in one direction. You move forward into a future you have not yet seen, leaving behind a past you can no longer touch. General relativity does not describe time that way. In Einstein's universe, space and time are woven into a single four-dimensional fabric, and the path that any object traces through that fabric has a name. It is called a worldline. Your worldline began at your birth and extends, moment by moment, through every place you have ever been. It is the complete record of your existence, drawn as a curve through space-time. A closed time-like curve is a worldline that bites its own tail. Let the definition be exact, because precision is the entire point. A curve in space-time is called timelike when it stays everywhere within the local light cone. That means an object following it always moves slower than light, always experiences time ticking forward in its own frame, always behaves like ordinary matter rather than a beam of light or something faster. There is nothing exotic about a time-like curve. Yours is one. A closed time-like curve is simply a time-like curve that, after running forward in this perfectly normal way, returns to its own starting event. Same point in space, same point in time. The traveller never once exceeds the speed of light, never feels their clock run backward, and yet they arrive at the moment of their own departure. The loop closes. This is the rigorous geometry beneath the phrase, travel into the past. Not a wormhole in a film, a worldline that forms a ring. To see how a thing like that could even be possible, picture the light cone. Take any event in space-time, any single here and now. From it, light spreads outward into the future, tracing a cone. Light also converges from the past, tracing a second cone beneath. Everything you can ever affect lies inside your future cone. Everything that could ever have affected you lies inside your past cone. The walls of these cones are built from light itself. And because nothing outruns light, your worldline must always stay inside them, always pointing into the future. The cones are the guardrails of cause and effect. So long as they stand upright and orderly across space-time, the past stays behind you and the future stays ahead. But the cones are not nailed in place. Mass and energy curve space-time, and curved space-time tilts the cones. Near a dense, spinning object, the cones lean. They lean in the direction of the spin, dragged around like leaves caught in a slow whirlpool. This is real, measured physics. It is called frame dragging, the Lense-Thirring effect, and it has been confirmed in orbit around the Earth. Now imagine tilt growing. Imagine the cones leaning further and further until, at some critical place, a future cone has tipped so far that part of it dips down and reconnects with the past. Follow the cones around, always stepping into what is locally the future, and the geometry can quietly walk you back to where you started. Think of an escalator built into the side of a hill. You climb it the entire way, always stepping up, always moving forward, and it deposits you at the bottom of the same staircase you began on, because the hill itself was bent into a loop. Your steps were always upward, the landscape was the trick. That is a closed timelike curve. The traveller does nothing strange. Space-time does everything. The mathematics of this was not dreamed up by a science fiction writer. It was discovered by one of the most rigorous minds of the 20th century, and he discovered it almost by accident, while thinking about the nature of time itself. His name was Kurt Gödel. Born in 1906, an Austrian-American logician working at the Institute for Advanced Study in Princeton, Gödel had already changed the history of thought once by proving that any sufficiently rich system of mathematics must contain true statements it can never prove. He was a careful man, a quiet man, and a close friend of Albert Einstein, with whom he walked home most days. In 1949, for a volume celebrating Einstein's 70th birthday, Gödel gave an unusual gift. He had taken Einstein's field equations and found a new, exact solution to them. It described an entire universe. The universe Gödel described does not expand. It rotates. Imagine the whole of the cosmos turning slowly about every point, a homogeneous sea of matter, what physicists call pressureless dust, spinning against a balancing term in the equations. And here was the shock buried in the mathematics. In Gödel's rotating universe, closed timelike curves pass through every single point. Not in some far corner, everywhere. From any event, in principle, a path exists that loops back to the past. Einstein's equations, the bedrock of modern cosmology, permitted a universe in which the past was not closed off at all, but accessible, lying at the end of a long enough journey. The rotation rate sits in a clean expression. Omega equals 2 times the square root of pi g rho. Omega is the angular velocity of the cosmos. G is Newton's gravitational constant, and rho is the mean density of matter. The equation simply states the spin required to balance the model, the rate at which the whole universe would have to turn. Keep that quantity in mind. We will need it later. Because whether the real universe spins at anything like this rate turns out to be a question we can actually measure, and the answer will matter enormously. Gödel himself did not read his discovery as an invitation to build a time machine. He read it as a statement about the nature of time. In a companion essay written the same year, titled A Remark About the Relationship Between Relativity Theory and Idealistic Philosophy, Gödel argued that if the laws of physics permit a universe in which one can travel into one's own past, then the passage of time cannot be a fundamental, objective feature of reality. Time, he suggested, is something of an illusion. The flow we feel, the sense that the present is real while the past has vanished, must be a feature of our experience, not of the cosmos itself. What does it mean that the man who found the loops concluded not that we could ride them, but that time itself was not what we thought it was? Hold that question. The whole argument will circle back to it. To understand why Gödel reached for that conclusion, we have to step back to a much older idea about time, one that general relativity quietly revived. It is called the block universe. The block universe, also known as Eternalism, is the view that past, present and future all exist, equally and at once. There is no special moment called now that is more real than any other. Instead, all of space-time exists as a single, unchanging, four-dimensional whole, like a vast loaf of bread in which every slice, every moment of history is already there. Your birth, this sentence, your death, the heat death of the cosmos, all of it laid out in the loaf, none of it coming into being or passing away. What we call the flow of time is, in this picture, the slow travel of consciousness along a world line already drawn in full. This is not mysticism. It is, many physicists argue, the most natural reading of Einstein's relativity. Back in 1908, the mathematician Hermann Minkowski took Einstein's special relativity and recast it as a geometry of 4 dimensions, declaring that space by itself and time by itself were doomed to fade into mere shadows, and only their union would endure. Relativity showed that two observers moving differently will disagree about which events happen at the same time. There is no universal present that everyone shares. And if there is no objective, universe-wide now, then the division of time into a real present, a vanished past, and an open future loses its footing. What remains is the block. Every event equally existing, fixed in its place in the 4-dimensional whole. The philosophical roots run deeper still, back through the philosopher John McTaggart, who in 1908 argued for the unreality of time, and further back to the ancient Greek Parmenides, who held that genuine being does not change, that reality is one, whole, and unchanging. It is worth setting the block universe against its rival, because the contrast sharpens everything that follows. The opposing view is called presentism, the common-sense belief that only the present moment is real, that the past has ceased to exist and the future has not yet come into being, that reality is a thin, moving edge of now advancing through time. Presentism matches how time feels, but it sits uneasily with relativity, because relativity denies that there is any single universe-wide now for the edge to be. Two observers in motion, relative to each other, will slice space-time into moments differently. An event that is present for one can lie in the past or the future of the other. If no two observers can even agree on what counts as the present, then a single advancing edge of now, shared by all of reality, has nothing to stand on. The block universe, in which all moments simply exist, requires no shared present, and so survives where presentism strains. This is why so many physicists regard eternalism as the natural reading of Einstein's theory. And it is the soil in which closed time-like curves quietly take root. What does it mean that our most successful theory of time describes a reality in which the flow we feel most certainly may be the one thing that is not really there? Notice how naturally closed time-like curves and the block universe fit together. If all moments already exist, then a loop in time is not a contradiction. It is just a worldline shaped like a ring inside a structure where every part is permanent. The traveller who returns to their own past does not change anything, because in the block there is nothing to change. The past is not rewritten. It was always exactly as it is, traveller included. This is the seed of the entire investigation, and we will return to it with full force. In a block universe, a closed time-like curve threatens no paradox at all. It is simply part of the fixed, frozen shape of things. Gödel's was not the only solution hiding these loops, and it was not even the first. The honour of the earliest known example belongs to a more obscure piece of work. In 1937, a physicist named Willem Jacob van Stockum published an exact solution describing an infinitely long cylinder of dust rotating rigidly about its axis. The work built on earlier mathematics from Cornelius Lanczos, who had written down the relevant rotating dust solution as far back as 1924, holding mathematical priority, though the causal strangeness was not yet recognized. In van Stockum's spinning cylinder, something remarkable happens to the geometry as you move outward. Beyond a certain rotation threshold, one of the directions of space, the direction that circles the axis, tilts until it becomes timelike. A coefficient in the metric, written as L equals r squared times the quantity 1 minus a squared r squared, changes sign. When that coefficient flips, the circular direction around the cylinder is no longer a loop through space. It is a loop through time. Travel around the cylinder, and you travel around in time, back to where and when you began. So even before Gödel handed Einstein his birthday gift, the field equations had already whispered that rotation, enough of it, concentrated enough, could bend the cones until the past lay in a circle around an axis. These were not popular results. They sat in the technical literature, curiosities, mathematical possibilities that most physicists assumed could never describe anything real. Then, in 1974, a young physicist named Frank Tipler took the idea and gave it a sharper edge. Tipler analyzed a massive, infinitely long, extraordinarily dense cylinder rotating at enormous speed, and showed in detail how its frame dragging would tilt the surrounding light cones far enough to create closed, time-like curves in the space around it. The popular descriptions that grew up around Tipler's analysis cite a structure of staggering specifications, a total mass exceeding 10 times the mass of our Sun, that is, more than 2 times 10 to the 31st kilograms, roughly 4 times 10 to the 31st pounds. Densities approaching those inside a neutron star, where a sugar cube of matter outweighs a mountain. Angular velocities on the order of billions of revolutions, and a length that, in the clean version of the mathematics, is infinite. That word, infinite, is where the trouble starts. And it is the first of many places where these loops begin to look less like engineering blueprints and more like mathematical mirages. An infinitely long cylinder cannot be built. The universe does not contain infinite material, and even if you tried to make the cylinder finite, the analysis suggests the geometry no longer cooperates in the same clean way. We will return in time to just how fragile every one of these constructions turns out to be. For now, simply notice the pattern beginning to form. Every road to the past that general relativity permits comes with a price tag attached, and the prices are strange. Infinite length, impossible density, conditions that may exist nowhere in the real cosmos. Keep that pattern in mind. It is not an accident, and by the end, it will start to look like a message. It is worth taking a moment on the sheer scales involved, because they tell their own quiet story. One might assume that if closed time-like curves are this elusive, they must hide at the unimaginably small Planck length, the scale of about 1.5 times 10 to the minus 35 meters, roughly 6 times 10 to the minus 34 inches, where the smooth geometry of space-time is thought to dissolve into quantum foam, far below anything we could ever probe. That would be one way to keep them safely out of reach. But that is not where they sit. In a rotating black hole of ordinary stellar mass, the closed time-like curve region lies not at the Planck scale at all, but at a macroscopic distance from the ring singularity, a region large enough to fly a ship through, if only it were not sealed behind lethal horizons. The loops are not hidden by being too small. They are hidden by being walled off. And Gödel's cosmic loops run to the opposite extreme of scale. To ride one, you would have to journey out beyond the surface where the cones tip past the speed of light, across distances that dwarf the observable universe itself, whose radius runs to about 4 times 10 to the 26th meters, some 46 billion light-years in every direction. Picture a marine biologist who has mapped every current of a single lagoon, only to be told the lagoon opens onto an ocean billions of miles wide. Everything she learned about the lagoon stays true. None of it describes the ocean. The loops live out in that ocean, or locked in a vault we cannot open. And either way, the message is the same. Present in the equations, absent from the world. It is worth pausing on the precise shape of Gödel's solution, because the mathematics carries the whole strangeness in a single line. The geometry of his universe is written in what physicists call a line element, the rule that tells you the space-time distance between any two nearby events. Gödel's line element reads, in words, ds squared equals a squared times the quantity dt squared minus dx squared plus 1/2 e to the 2x dy squared minus dz squared plus 2e to the x dt dy. Most of that looks like ordinary spacetime. The danger hides in the very last piece, the cross term that mixes dt, a step in time, with dy, a step in space. That mixing is the mathematical fingerprint of the spinning cosmos, and it is exactly what tilts the light cones as you move outward, leaning them further and further until, past a critical distance, they have tipped enough for a path to circle back on its own past. The loops in Gödel's universe are not nearby. They are what physicists call topologically large. To ride one, you would have to travel an immense distance, out beyond the surface where the cones have tipped past the speed of light, on a journey requiring more fuel than any conceivable craft could carry. The past is reachable in principle and impossibly far in practice. That gap between what the equations permit and what the universe allows is the gap this entire exploration lives inside. It is also worth being clear about who Gödel was, because it shapes how we should read his conclusion. This was not a fringe figure. Kurt Gödel is regarded by many as the greatest logician since Aristotle. His incompleteness theorems, proved in 1931, set permanent limits on what mathematics can prove about itself, and shook the foundations of the field. When a mind of that caliber, working with Einstein's own equations, concluded that the lawful possibility of looping back to the past meant that the flow of time was not fundamental, the conclusion deserves to be weighed, not waved away. He did not say time travel was easy. He said that if the equations permit it even in principle, then our deepest intuition about time, that the present is uniquely real and the past is gone, cannot be a feature of the cosmos itself. The block was, for Gödel, the honest reading of the physics. We will see near the end that he drew from this a further conclusion that almost no one quotes, and that it points in a direction the popular telling never mentions. For now, hold only the facts presented plainly as they stand in the mainstream literature. General relativity, the most successful theory of gravity ever written, the theory confirmed to exquisite precision by the bending of starlight, the slowing of clocks, and the ripples of gravitational waves detected in 2015, also permits closed timelike curves. They appear in Gödel's rotating universe. They appear around van Stockum's and Tipler's spinning cylinders. They are exact solutions to Einstein's equations, as mathematically valid as the orbit of a planet or the fall of an apple. The theory does not forbid the past. It leaves the door, at least on paper, ajar. What does it mean that our best theory of space and time contains, woven into its own equations, the possibility of loops back to the beginning? That is the question we will spend the rest of this exploration trying to answer honestly. And the honest answer, as we will see, is far stranger and far quieter than time travel. It is the answer of the dead-end street. If rotating universes and infinite cylinders feel too remote, the field offers closer, sharper constructions, each one a different attempt to fold space-time into a loop, and each one revealing something new about why the cosmos seems so reluctant to allow it. Consider first the most elegant of them, because it needs no exotic ingredients at all. In 1991, the Princeton astrophysicist J. Richard Gott III published a paper in Physical Review Letters describing a time machine made from cosmic strings. A cosmic string is a hypothetical relic of the early universe, a thread of concentrated energy, thinner than an atom, but cosmically long, predicted by certain theories of how matter behaves at enormous energies. A cosmic string does something peculiar to the space around it. It does not curve space in the ordinary way. Instead, it removes a wedge. Space around a cosmic string is flat, but a slice of angle is missing, as if you cut a thin pie slice out of a flat sheet of paper and then taped the cut edges together. The sheet is still flat everywhere, but it now forms a shallow cone, and the total angle around the string is less than the full 360 degrees. The size of the missing wedge is given by a clean expression, the deficit angle. D equals 8 pi g mu, where g is again Newton's gravitational constant and mu is the mass per unit length of the string. The more massive the string, the wider the wedge it cuts from space. Gott showed something startling. Take two such cosmic strings and send them flying past each other at high speed, close to the speed of light. Because of the missing wedges and the way relativity treats simultaneity for fast-moving objects, a path can be found that loops around both strings as they pass and returns to its own past. No exotic matter, no singularities, no horizons. Just two ordinary, if hypothetical, strings, moving fast, their conical shortcuts adding together into a closed, timelike curve. Gott's condition was precise, requiring the strings to move faster than a threshold set by their deficit angles. For a moment, in the spring of 1991, it looked as though the cleanest possible time machine had been found, and Gott's work reached the cover of Time magazine that May. But examine the construction closely, and the now familiar price tag appears. The strings, in Gott's clean solution, must be infinitely long. Try to use finite strings, a closed loop of cosmic string instead, and the analysis shows the loop has so much mass energy that it collapses into a black hole before it can ever function as a time machine, trapping any would-be traveler behind an event horizon. Other physicists, examining the two-string system, found that in an open universe, there is simply never enough total energy available to accelerate the strings to the required velocity. The center of mass of Gott's configuration, it turned out, behaves in a way that cannot be reached. The loop is there in the mathematics. The road to building it keeps dissolving. The same story repeats with the most famous time machine proposal of all, the wormhole. In 1988, Michael Morris, Kip Thorne, and Ulvi Yurtsever published a landmark paper in Physical Review Letters. Thorne, who would later share the Nobel Prize for detecting gravitational waves, had been prompted by a question from the astronomer Carl Sagan, who wanted a scientifically defensible way to move a character across the galaxy in a novel. What Thorne and his colleagues worked out was this: a traversable wormhole, a tunnel connecting two distant regions of space-time, could, in principle, be turned into a time machine. Take one mouth of the wormhole and move it on a fast round trip close to light speed. Relativity dictates that the moving mouth ages more slowly than the stationary one. When the two mouths are brought back together, they no longer agree on what time it is. Step through in one direction and you step into the past. The wormhole, then, can be a doorway in time, but only if it can be held open. And here, the toll is the steepest yet. To keep a wormhole's throat from pinching shut in an instant, you need a particular kind of matter threading it, matter with negative energy density, what the literature calls exotic matter. This is matter that violates what physicists call the energy conditions, the rules that ordinary matter and energy obey. The relevant one here is the null energy condition, written compactly as T mu nu, contracted with a null vector k being greater than or equal to 0. In plain terms, the energy conditions encode the statement that energy density, as measured by the relevant observers, is not negative. Every form of ordinary matter respects them. The exotic matter required to hold a wormhole open must break them. And while quantum effects like the Casimir effect can produce tiny, fleeting amounts of negative energy, nothing in known physics provides the quantity, stability, and arrangement a wormhole would demand. Once again, the loop exists on paper. The material to build it does not appear to exist at all. There is one place, though, where closed time-like curves are not built but found, lurking inside an object we have good reason to think is real: a rotating black hole. The exact solution for a spinning black hole was discovered by Roy Kerr in 1963, and when physicists mapped its interior, they found that deep inside, surrounding the ring-shaped singularity at its heart, there is a region where the geometry tilts so severely that closed time-like curves appear naturally. No exotic matter required. The rotation of the black hole does it. In the mathematics, that circling direction around the ring becomes timelike, exactly as in Van Stockum's cylinder. Whether this is expressed through the metric component g phi phi turning negative, which is the technical signal that the angular direction has become a direction in time, the conclusion is the same. A real astrophysical object, the kind we have now photographed, contains regions where the past lies in a loop. So why can we not simply fly a spacecraft into a spinning black hole and circle into yesterday? Because the loops are sealed away. The closed Timelike curve region inside a Kerr black hole lies deep within, beyond not one but two horizons: the outer event horizon, the point of no return, and an inner boundary called the Cauchy horizon. The Cauchy horizon is where predictability itself breaks down, where the orderly unfolding of cause and effect from past to future loses its grip. And there is strong reason to believe that the Cauchy horizon is not a place a traveller could ever survive or even reach intact. Matter and radiation falling in pile up against it, blue-shifted to enormous energies in a runaway process known as mass inflation. The leading expectation is that the Cauchy horizon is unstable, that it would buckle into a genuine lethal singularity under the slightest real-world disturbance. The loops are there, but they are caged, walled off behind horizons in a region the universe appears to have sealed shut. What does it mean that the one realistic object containing closed time-like curves keeps them locked in its most inaccessible vault? Set aside for a while the question of whether these loops can be built or reached, and ask a different one. Suppose, somehow, you found yourself on a closed time-like curve. What could you actually do? Could you change the past? Could you walk into yesterday and prevent your own journey, the famous grandfather paradox, in which a traveller undoes the very cause of their travel? Here the physics gives a remarkably firm and remarkably strange answer, and it is the heart of our story. The answer was crystallized in the mid-1980s by the Russian physicist Igor Novikov, working in the tradition of the great Moscow School of Cosmology around Yakov Zeldovich. It is called the Novikov self-consistency principle, and it states, in Novikov's words, that the only solutions to the laws of physics that can occur locally in the real universe are those which are globally self-consistent. Put more simply, events on a closed time-like curve are allowed to happen only if they are consistent with the history that produced them. You cannot kill your grandfather because he was not killed. The past already contains whatever you will do when you travel to it. If you go back, you were always there. Your actions in the past are not additions to history. They are part of it, and always were. Any sequence of events that would create a contradiction simply has probability 0. It does not occur. The universe, on this principle, permits the loop but forbids the paradox. Novikov's collaborators gave the idea a haunting name. In a 1992 paper, the self-existent objects and pieces of information caught in such loops, things that exist without ever having been created, were called jinn, after the spirits of old stories that have no birth. We will return to those jinn because they will turn out to matter far more than they first appear. It is worth asking how seriously to take self-consistency. In 1991, Thorne and two younger colleagues, Fernando Echeverria and Gunnar Klinkhammer, tested it with the simplest possible physical system, a billiard ball. Imagine a billiard ball rolling toward a wormhole time machine. It enters one mouth, emerges from the other in the past, and, if aimed correctly, strikes its earlier self, knocking it off course so that it never enters the wormhole in the first place. The classic paradox, rendered in ivory and felt. What Echeverria, Klinkhammer and Thorne discovered when they worked through the mathematics was not that the paradox was impossible. It was something far more unsettling. They found that for the very same initial setup, the same ball aimed the same way, there exist multiple self-consistent solutions. The ball can glance off itself just gently enough that it still enters the wormhole and emerges to deliver exactly that gentle glancing blow. And there is not just one such consistent history. There are many. In some versions of the analysis, infinitely many. Sit with the strangeness of that. We are taught that classical physics is deterministic, that a given starting condition leads to exactly one outcome, the future fixed by the present, like the next frame of a film. A closed time-like curve breaks this, but not in the way anyone expected. It does not leave the system with no solution. It leaves it with too many. Determinism fails not by absence, but by overabundance. A single setup blossoming into a fan of equally valid, equally self-consistent histories. The loop does not destroy the laws of physics. It floods them with answers. Keep that flood in mind. It will matter when we ask what, exactly, a loop like this could ever explain. When physicists carried the question into the quantum world, the answer grew stranger still and pointed in a single, consistent direction. In 1991, the Oxford physicist David Deutsch, one of the founders of quantum computing, asked what quantum mechanics does on a closed time-like curve. He formulated a consistency condition. The quantum state circulating in the loop must be a fixed point, a state that comes out of the loop exactly as it went in, so that the history is self-consistent. In the compact language of the field, the loop's density matrix must satisfy a self-consistency equation, expressed as the partial trace over the external system of the evolution operator acting on the combined state, returning the original looped state unchanged. Deutsch proved that such a fixed point always exists. Quantum mechanics, unlike classical physics, can always find a self-consistent solution. There is always an answer. But the answer comes at a devastating cost to anyone hoping to use the loop. Deutsch's model shows that when you send a pure quantum state, a state carrying definite, specific information, around a closed time-like curve, it does not come back pure. It comes back mixed. The cleanest example? Feed in a qubit in a sharp, definite superposition, and the loop returns it as the maximally mixed state, written as 1/2 times the identity, which is to say, pure noise, a coin flip, all original information scrambled away. The loop launders information. Whatever specific message you try to send around it emerges as randomness. Entanglement with the outside world is broken. The looped system is sealed off informationally from everything else. This is the formal heart of the dead-end street, and it deserves to be named plainly. A closed time-like curve in Deutsch's quantum treatment has zero capacity to create or transmit genuinely new information. It can only represent in scrambled form, what the self-consistency condition already fixed. A particle traversing the loop must be, in the language of the mathematics, an eigenstate of the once-around evolution, a state invariant under the trip. Nothing new survives the journey. We will return to this with full force, because it is the single most important fact in this entire investigation, and it cuts against a claim that some have built upon these loops, a claim we have not yet examined. In 1994, the Nobel laureate H. David Politzer probed Deutsch's model further and found additional cracks, showing that for certain inputs, the prescription no longer fixes a unique output, posing, in his words, serious problems for the statistical interpretation of quantum theory. The loops do not behave like ordinary physics. They strain the very framework we use to make predictions. By now, you can feel the weight of accumulating evidence, all of it pointing the same way. The universe seems to tolerate these loops only by stripping them of any power to do anything. And this brings us to the most direct attempt anyone has made to slam the door entirely. In 1991 and 1992, Stephen Hawking proposed what he called the chronology protection conjecture. Its statement is blunt. The laws of physics do not allow the appearance of closed timelike curves, and so, in Hawking's memorable phrase, they make the universe safe for historians. Hawking proposed a mechanism. As a time machine is on the verge of forming, at the boundary he called the chronology horizon, quantum fields fill the region. Their energy, properly calculated, does not stay finite. It diverges, climbing toward infinity. And that runaway energy, feeding back into the geometry through gravity, would destroy the time machine at the very instant it tried to form. The universe, on this view, defends its own causal order, snuffing out every loop before it can close. It is a beautiful idea. Hawking even spoke, half in jest, of a chronology protection agency standing guard over the timeline. And here we must be scrupulously careful, because the conjecture is exactly that, a conjecture, and it is one of the open frontiers of physics rather than a settled law. No general proof of chronology protection has ever been given. Worse for the idea, specific spacetimes have been found in which the quantum energy at the chronology horizon does not diverge, directly contradicting Hawking's proposed mechanism. And in 1998, in a paper with Michael Cassidy, Hawking himself examined models of chronology selection and conceded in print that the back reaction does not enforce chronology protection. The very mechanism he had proposed did not, in the end, do the job he proposed it for. The reviews of the field, written since, repeatedly call the matter unsettled, noting that there is no consensus on the quantum instability of the relevant horizon, and that its present status remains quite unclear, with many physicists believing that only a complete theory of quantum gravity, which we do not have, could settle the question. We will come back to that deferral, because it carries more weight than it seems. Even with Hawking's specific mechanism in doubt, the broader instinct behind chronology protection found other defenders. The physicist Matt Visser, who has spent much of his career studying wormholes and the conditions for time travel, argued for what he called a defense in depth, the idea that even if one barrier against the loops fails, Others stand behind it, that the universe has, as it were, layered its protections so that the formation of a closed time-like curve would have to defeat not one obstacle, but a succession of them. Yet, a defense in depth is a description of a hope as much as a proof. It catalogues reasons the loops seem hard to make. It does not demonstrate that they are impossible, and the honest reviews say so plainly. So far, in the literature's own words, no proof of the chronology protection conjecture has been given. There seems, another review states, no consensus on the quantum instability of the relevant horizon. Its present status, a third concludes, remains quite unclear. These are not the words of a settled science. They are the words of a field standing at the edge of what its current theories can decide. It is worth giving the loops a precise definition, because precision is what keeps this honest. Physicists describe the region where causality breaks as the chronology-violating set, written as the union, over all points, of the overlap between a point's causal future and its causal past, the set of events that lie both in your future and in your own past at once. Where that set is empty, the universe is orderly, and cause precedes effect everywhere. Where it is not empty, closed time-like curves thread through it. The whole debate over chronology protection is, at bottom, a debate over whether the laws of physics permit that set to be anything other than empty in the real world. And the striking fact, the one too rarely stated plainly, is that after more than half a century of work, the answer is not known. What does it mean that our finest theories of space, time, and matter cannot yet tell us whether the past is permanently closed or merely guarded? There is one more thread to lay down, and it is perhaps the most curious of all, because it argues against these loops not from physics, but from logic. In 2008 and 2009, the computer scientists Scott Aaronson and John Watrous asked what a computer could do if it had access to a closed time-like curve. The answer was almost comical in its excess. A computer with a closed time-like curve, they proved, could solve an entire class of fearsomely hard problems, the class known as PSPACE, in a flash. Both ordinary classical computing and the full power of quantum computing would collapse down to this single, vastly more powerful level. Such a machine could play perfect chess on a board of any size, solve problems that would take an ordinary computer longer than the age of the universe, almost as easily as adding two numbers. Aaronson's own reading of this result is telling, and we will return to it. A device this absurdly powerful is, in his judgment, evidence that closed time-like curves do not physically exist. The loops would make the world too easy. Reality does not appear to be that easy. Around these central ideas orbit still stranger possibilities, each adding to the picture. There are Malamant-Hogarth spacetimes, geometries in which an observer could, in a finite amount of their own time, witness the entire infinite future of another observer, opening the door to a kind of hyper-computation that could, in principle, decide questions no ordinary computer ever could. There are modified theories of gravity, like Einstein-Cartan theory, which adds the twisting of spacetime called torsion, and in which, some analyses suggest, the torsion generated by the spin of matter could itself act as a natural chronology protector, suppressing the loops. And there is string theory, and its higher dimensional cousin, M theory, where Gödel-like solutions reappear in 5 dimensions, only to be expelled again when the geometry is lifted into higher dimensions, leading some to speak of a holographic protection of chronology. The deepest theories we have seeming to push the loops back out the door whenever they appear. It helps to see, even briefly, how the Kerr black hole hides its loops in the mathematics, because it is the same trick every time. The geometry of a spinning black hole is written most often in coordinates named for Boyer and Lindbergh, and one component of that geometry, the term physicists label G phi phi, governs the circular direction that wraps around the hole's axis. Spoken aloud, the expression runs G phi phi equals the quantity minus r squared plus a squared squared plus delta a squared sine squared theta, all divided by sigma times sine squared theta, where a measures the spin and the other symbols track position. The detail that matters is simple. Ordinarily, G phi phi is positive, marking the circular direction as a direction through space. But close to the ring singularity, in the deep interior, that term can turn negative. And when it does, the circle around the ring is no longer a loop through space. It is a loop through time. The black hole's rotation has tilted the cone so far that going around becomes going around in time. The same sign flip we saw in Van Stockum's cylinder, now buried at the center of an object we have genuinely observed. The closer physicists have looked at every proposed route to the past, the more uniform the verdict has become. Each one fails for a different, specific, almost tailored reason. Consider the one experimental proposal that reached public attention. The physicist Ronald Mallet spent years developing a design for a time machine built from a circulating beam of laser light, arguing that intense, ring-shaped light could drag space-time around it strongly enough to seed closed time-like curves. It is a serious, imaginative idea. But when Ken Olam and Alan Everett examined it carefully in 2005, they found 2 fatal problems. First, Mallet's spacetime contains a singularity on its axis even when the laser is switched off, which means it does not describe what it claims to. And second, and more devastating, for any realistic intensity of light, the closed time-like curves Mallet's design would produce do not appear nearby at all. They appear, in Olam and Everett's analysis, at distances from the axis greater than the radius of the entire visible universe, by an immense factor. The loop is in the equations. To reach it, you would have to cross more space than exists within our cosmic horizon. The price tag again, written this time in a distance no one could ever pay. Then there are the constructions that push past the edges of known physics, and they only deepen the pattern. There are space-times, named for the physicists David Malamant and Mark Hogarth, with a causal structure so strange that an observer falling toward a particular point could witness, in a finite span of their own time, the entire infinite future of another observer. In such a geometry, one could, in principle, set a computer running on a problem with no time limit, fall toward the special point, and receive the answer to a question that would otherwise take forever. A feat the literature calls hypercomputation, capable in principle of settling problems no ordinary computer could ever decide, including the famous halting problem of whether a given program will ever stop. It is a breathtaking possibility, and it is also, most physicists suspect, a sign that something has gone wrong, that a geometry permitting it is telling us more about the limits of our equations than about anything buildable. Some have asked whether modifying gravity itself could rule the loops out from the start. In a theory called Einstein-Cartan, an extension of general relativity that allows space-time not only to curve, but to twist, a twisting fed by the intrinsic spin of matter, the physicist Harold Soleng showed in 1993 that the closed timelike curves around a spinning string appear only when the spin density is pushed to an extreme, so high that the energy of the spin overwhelms the ordinary energy of the matter. Below that threshold, the twisting of space-time acts, in effect, as a natural guardian against the loops, suppressing them before they can form. The deeper theory on this reading leans against chronology violation rather than toward it. The deepest theories we have lean the same way. In string theory, and in its higher dimensional completion known as M-theory, Gödel-like solutions containing closed timelike curves do appear in 5 dimensions, in geometries with names like Kurt Gödel. But something instructive happens when physicists examine them with the full machinery of the theory. Analyses of these supersymmetric Gödel universes, probing them with the extended objects string theory permits, have found that certain of them are simply not valid backgrounds for the theory at all. And when the geometries are lifted into still higher dimensions, the loops can vanish, dissolved by the change in perspective, in what some researchers have called a holographic protection of chronology, where over-rotation tries to expose closed timelike curves to the outside. The consistency of the theory, its unitarity, breaks down, as if the framework itself refuses to permit it. Time and again, the more complete the theory, the more firmly it shows the loops the door. And, lest all of this seem purely theoretical, the closed timelike curve has even reached the laboratory bench, though not as a true time machine. In 2018, the physicists Martin Vasquez and Sabin proposed quantum and classical simulators of closed timelike curves, systems engineered to mimic the mathematics of a loop in time, complete with an analogue of the chronology protection mechanism that suppresses the paradoxical cases. And experimental groups, including the team around Timothy Ralph at the University of Queensland, have run photonic simulations of Deutsch's quantum loop, using particles of light to act out the self-consistency condition, and watch, in the safety of the lab, how a state sent around the simulated loop is scrubbed of its information exactly as Deutsch's theorem predicts. No one has built a real time machine, and nothing in these experiments transmits anything into the actual past. What they confirm is subtler and, for our story, more important. When you faithfully model the mathematics of a closed timelike curve, the loop behaves precisely as the dead-end picture says it must. Consistent, sterile, producing nothing new. What does it mean that every road to the past, examined closely, dissolves before you can walk it? And that the closer the model comes to reality, the more completely the loop is robbed of any power to do, to change, or to create. That is not the behavior of a doorway. It is the behavior of a wall with a picture of a door painted on it. Through all of it, one question has been waiting. The question Gödel raised at the very start. Does the real universe rotate? Because if it does not, then Gödel's cosmos, the cleanest home for closed timelike curves on the largest scale, is not our home. And this we can measure. The light of the cosmic microwave background, the faint afterglow of the early universe, carries the fingerprints of any large-scale rotation or lopsidedness in the cosmos. Instruments built to read that light, NASA's COBE satellite in the early 1990s, then WMAP, and most precisely the European Space Agency's Planck satellite, have searched for exactly this signature. In 2016, a team led by Daniela Sade at University College London published the most stringent answer yet. They found that a rotating, anisotropic universe is, in their words, strongly disfavored, with odds of 121,000 to 1 against. The bound they placed on any cosmic rotation relative to the expansion of the universe was smaller than 5 parts in 100 billion. Keep that number close. The universe, as far as our finest instruments can tell, does not spin. Gödel's beautiful solution, the one he handed Einstein, describes a cosmos that is not the one we live in. Remember that the door he opened was real. Remember, too, that the measurements have been quietly closing it. For the length of this exploration, I have laid out the evidence plainly, the way it sits in the scientific literature. General relativity permits closed timelike curves. They appear in Gödel's rotating universe, around than Stockham's and Tipler's cylinders, in Gott's flying cosmic strings, in the throats of wormholes, and inside the sealed hearts of Kerr black holes. I have not yet challenged a single claim. Now we test them, because around these strange and beautiful loops, certain larger claims have grown. Claims that reach beyond physics and into the oldest questions of all. And those claims do not survive the examination as cleanly as their advocates suppose. Begin with the boldest. Recall the djinn, those objects and pieces of information that Novikov's collaborators named, the things caught in a closed timelike curve that exist without ever having been created. This is sometimes called the Bootstrap paradox. Picture a man who receives the blueprints for a time machine from a stranger, builds the machine, travels into the past, and hands the blueprints to his younger self, who will one day become the stranger. The loop is self-consistent. Novikov's principle is satisfied. And yet ask the simple question, who designed the machine? No one. The blueprints were never invented. They simply circulate in the loop, uncaused, self-existing, information that came from nowhere. Here is where the claim is made, and I will state it in its strongest form, because a fair hearing demands it. Some who popularize these ideas argue that the bootstrap loop shows something profound, that existence does not need a first cause after all. If information, even objects, can simply exist in a self-consistent loop without ever being created, then perhaps the universe itself needs no creator. Perhaps being can bootstrap itself into existence, caused by nothing outside itself, explained entirely from within. The closed time-like curve on this reading becomes a kind of proof that something can come from nothing, that the chain of cause and effect can close into a circle and need no external source. It is an elegant thought. It has been presented in various forms as a way the deepest question, why is there something rather than nothing, might dissolve. Now examine it, and notice first that the physics we have already covered does not support this claim. It demolishes it. Recall what Deutsch proved about the quantum loop. A closed time-like curve cannot create new information. Feed in a definite, specific state, and it returns as noise, the maximally mixed one-half identity. Every original bit scrambled to randomness. The loop's content is not generated by the loop. It is fixed in advance by the self-consistency condition, and the loop merely represents it. Recall what Echeverria, Klinkhammer and Thorne found classically. The loop does not produce a unique new history. It admits a flood of pre-existing consistent ones. In every formulation, classical and quantum, the closed time-like curve has exactly zero capacity to originate anything. It is, in the most literal information-theoretic sense, sterile. The blueprints in the bootstrap loop are not explained by the loop. They are smuggled in as a brute, unexplained given, and the loop simply carries them around forever. The philosopher David Lewis, who thought more carefully about time travel loops than almost anyone, said exactly this. Such information is, in his word, inexplicable. It comes from nowhere, and the source of the knowledge, as the analysis puts it, vanishes. Sit with what that admission means, because it is fatal to the claim built on it. To say the information is inexplicable is not to explain it. It is to confess that no explanation exists. The bootstrap loop does not answer the question of origin. It hides the question inside a circle and hopes no one looks. What does it mean when an explanation, examined closely, turns out to be the precise refusal to explain? It means it was never an explanation at all. And there is a deeper failure still, one that no amount of looping can repair. Suppose, for the sake of argument, that a self-consistent causal loop could exist exactly as described. What would it require in order to exist? It would require space-time already present, with its geometry already curved into the necessary shape. It would require matter and energy already existing to travel the loop. It would require the laws of physics already in force to govern the whole arrangement. The loop does not create these, it presumes them. The closed time-like curve is not a foundation on which existence can rest. It is a structure built on a foundation that must already be there. You cannot bootstrap a universe with a loop inside the universe, any more than you can lift yourself off the ground by pulling on your own feet. The loop is a finite circle of dependence, and a circle of dependent things, however cleverly closed, still depends as a whole on something beyond it. It does not ground itself. It cannot. Nothing that requires a stage already built can be the explanation for the stage. This is the ancient logic of cause and the loops. Only sharpen it. Nothing comes from absolute nothing. Zero added to zero remains zero. If there had ever been true nothingness, no space, no time, no matter, no laws, no loops, then nothing would exist now, because nothingness has no power to produce anything. Yet things exist. Therefore, something has always existed, something uncaused, something that did not depend on a prior cause or a surrounding stage. The only question worth asking is what that something is. And a closed time-like curve, which the physics itself proves can generate nothing, transmit nothing, and ground nothing, is the worst possible candidate for the role. The loop is not the uncaused cause. The loop is the clearest demonstration we have that mere geometry, however exotic, creates nothing on its own. Turn now to the second claim, quieter but more seductive, and the one that drew Gödel himself. It concerns the block universe. We saw that closed time-like curves fit naturally into eternalism, the view that all moments, past, present and future, exist equally in a single four-dimensional whole. And from this, an argument is sometimes drawn that if the universe is a timeless, self-contained block, with all of its history laid out at once, and nothing ever coming into being, then it needs no creator and no sustainer. A static, eternal block, the reasoning goes, simply is. It had no beginning in time to be caused, because time is internal to it. It needs nothing to hold it in being, because it does not change. The block universe, on this reading, is presented as a cosmos that explains itself by being timeless. Give the argument its due. It is more sophisticated than the Bootstrap claim, and it rests on real physics, the genuine relativity of simultaneity, the genuine four-dimensional geometry of Minkowski and Einstein. But examine what it actually establishes and what it quietly assumes. Eternalism is a thesis about the nature of time. It says that time is like space, that all moments are equally real, that there is no privileged flowing present. That is all it says. It is completely silent on a different and far deeper question. Why does the block exist at all? And why does it have the particular structure it has rather than some other? Calling the universe timeless does not make it self-explaining. A thing can be unchanging and still utterly dependent. Consider the abstract reasoning here carefully, because the argument trades on a hidden leap, the assumption that timelessness equals self-existence. But these are entirely different properties. To be timeless is to not change. To be self-existent is to require nothing outside oneself in order to be. A perfectly static, four-dimensional block of space-time, with its specific geometry, its specific contents, its specific laws, is still a particular thing that exists rather than not existing, and is one particular way rather than countless others it could have been. The question of why it exists and why it is this way remains entirely open. Removing the flow of time does not remove the need for a ground of being. It simply freezes the thing whose existence still cries out for explanation. And here the prosecution can call its most unexpected witness, Kurt Gödel himself. The man who gave us the rotating universe, the deepest mathematical home for closed time-like curves, the arch-eternalist who concluded from his own work that the passage of time is an illusion, was no materialist. Gödel was a committed Platonist. He believed that ultimate reality lay not in the physical block at all, but in a non-physical realm of necessary truths, and he held, in his private and philosophical writings, a conviction that mind and meaning were more fundamental than matter. The very physicist whose solution is invoked to argue for a self-sufficient material block did not believe the material block was self-sufficient, or fundamental, or all there is. What does it mean that the founder of the Eternalists' favorite cosmology looked through his own equations and saw, on the other side, not a self-explaining universe, but something beyond it? Now to the third claim, the one our instruments have already answered. And here the examination is briefest because the data is so blunt. To rescue the loops from irrelevance, or to argue that the special conditions of our universe are nothing special, one might appeal to grand alternatives. Perhaps the universe does rotate after all, making Gödel's cosmos real and its loops genuine. Or perhaps, in the language of the multiverse, there are countless universes with every possible configuration, and ours, with its particular conditions, is just one draw from an infinite deck, no design required. Examine the first, and the measurements have already spoken. We do not need to speculate about whether our universe rotates like Gödel's. We looked. The Planck satellite looked, and Kobe and WMAP before it. The verdict from Sade and her colleagues in 2016 is 121,000 to 1 against a rotating anisotropic cosmos, with any rotation bounded below 5 parts in 100 billion. The one large-scale cosmology that would make closed time-like curves natural is precisely the one the evidence excludes. The door Gödel opened, the real universe has been found to keep shut, not by a conjecture, but by observation. Examine the second, the multiverse, and notice what kind of move it is. The multiverse is proposed to explain away the apparent specialness of our conditions by drowning it in infinite alternatives. But not one of those other universes has ever been observed, measured, or detected, and by the very design of the idea, none ever could be. A proposal that no possible observation could confirm or refute is not a finding of science. It is a philosophical commitment wearing the costume of science. And here the prosecution can simply turn the most common accusation around. Critics of theism speak of a God of the gaps, an appeal to the divine wherever knowledge runs out. But what is an unobservable, untestable infinity of universes invoked precisely where the evidence for fine adjustment becomes uncomfortable, if not a naturalism of the gaps, an unfalsifiable entity summoned for the express purpose of avoiding the conclusion the data suggests. The maneuver theists are warned against is performed here in the other direction, and with far less evidence. And this exposes the last and most revealing pattern of all, the one that has been forming quietly since we first noticed the price tags on every time machine. Recall how the open questions of this field are so often answered. Why does chronology protection seem to hold, even though Hawking could not prove it and conceded his own mechanism failed? The reviews tell us a complete theory of quantum gravity, which we do not possess, would be required to settle it. Why are the loops sealed, sterile, walled off, excluded? We are told that future physics will explain it. Notice the structure of this answer. It is a promissory note, drawn on a bank that does not yet exist, payable at a date that never comes. We do not know yet, but science will figure it out, is not an argument. It is an act of faith. Faith in a future discovery, and it is no more rigorous than the appeal to gaps that its holders so often condemn. There is nothing wrong with saying we do not yet know. There is something deeply wrong with treating we do not yet know as though it were the same as the universe explains itself. There is a further argument hiding in the physics, and it works by following a claim to its breaking point. Return to what Aaronson and Watrous proved about computation. A computer with access to a closed Timelike curve could solve the entire class of PSPAC problems effortlessly, collapsing the hardest challenges in computer science to triviality. It could play flawless chess on a board of any size. It could crack problems that would otherwise outlast the universe. Now follow that to its conclusion. If such loops were real and accessible, the world would contain a shortcut around almost every hard problem there is. Reality would be, computationally, almost free. And reality is manifestly not free. The hardest problems stay hard. Aaronson draws the obvious inference, and it is a clean example of a reductio, an argument that refutes a premise by showing it leads to an absurdity. The sheer excessive power a closed time-like curve would confer is itself evidence that closed time-like curves do not physically exist. A thing that would make everything too easy is, by the very fact that nothing is that easy, almost certainly not there. The loop fails not only the test of construction and the test of information, it fails the test of a world that visibly resists us. And this lets us name the strangeness of the Bootstrap claim with full precision. The defenders of self-causation point to the loop and say, "See, the information needs no origin. It simply is." But ask the question they must answer and watch what happens. Where did the specific content come from? The exact blueprints, the precise message, the particular arrangement that circulates the loop. Not from the loop, which Deutsch proved creates nothing. Not from the traveller, who only carries it. Not from the past, which received it from the future, which received it from the past. The question is not answered. It is passed around the circle forever, like a debt that each party insists the next will pay, until you realize no one ever pays it. This is what it means to call the looped information inexplicable. It is not that the explanation is hard to find. It is that the structure is built specifically so that no explanation is ever required or ever given. What does it mean to offer, as the ground of all existence, the one arrangement designed never to account for itself? I return to this point often because it is where the dread of the subject finally turns into clarity. We are accustomed to thinking that a sufficiently clever structure, a loop, a self-reference, an infinity, might let the universe escape the need for a cause. The closed time-like curve is the most sophisticated such structure physics has ever produced, the very best candidate for a thing that causes itself. And when examined with full rigor, it does the opposite. It demonstrates in equations that geometry creates nothing, that self-consistency is not self-origination, that a circle of dependence is still, taken whole, dependent. The strongest case for a self-made cosmos becomes, on inspection, the strongest case against one. The loop was supposed to be the escape. It turned out to be the proof that there is no escape, that something uncaused before space and time must stand behind the whole arrangement for the arrangement to be there at all. So let us gather the verdict, because the evidence, examined honestly, all leans one way. The closed time-like curve was offered by some as a loophole in the deepest question, a way for being and information to exist without a cause, a way for the universe to ground itself in a self-consistent circle. The physics refuses the offer. Deutsch's theorem shows the loop creates no new information. The classical analysis shows it originates no new history. The bootstrap loop is, by its own defender's admission, inexplicable, which is to say, unexplained. The block universe, however timeless, remains a particular thing, whose existence and structure are not self-accounting. The one cosmology friendly to these loops has been excluded by Planck to one part in over 100,000. And the recurring promise that future physics will close every gap is faith, not finding. Strip it all away, and what remains is the oldest and simplest conclusion, made only sharper by these exotic loops. Something must exist that is genuinely uncaused, that depends on no stage already built, that requires nothing outside itself. A closed time-like curve cannot be that something, because the physics proves it produces nothing and presupposes everything. Unconscious geometry, unconscious matter, unconscious law, none of these grounds itself, and the loops are the proof, not the exception. What grounds existence must precede space-time, since space-time is the very thing in question. It must be powerful enough to be the source of all that depends on it. And in choosing this configuration of reality over the countless others the mathematics permits, configurations with loops and without, rotating and still, it must have done what only a will can do: select. This is the part that stays with me, not the loops themselves, strange as they are, The fact that the deepest thinker who ever drew one, Gödel, looked through it and saw not a self-made cosmos, but a mind behind the mathematics. Precision like that, selection like that, points past the geometry to something the geometry could never be. Power, knowledge, and will. An intelligent cause. Let me bring this exploration to a close. We began with a road that general relativity permits, but no traveller has ever found. The closed time-like curve, a world line that runs forward at less than the speed of light the entire way and still returns to its own past. We followed it through Kurt Gödel's rotating universe, the birthday gift he handed Einstein in 1949, in which loops to the past pass through every point. We traced it around Van Stockum's and Tipler's spinning cylinders, through Gott's flying cosmic strings, into the throats of Morris Thorne-Yurtsever wormholes held open by matter that may not exist, and down into the sealed interior of a Kerr black hole, where the loops lie caged behind horizons no traveller could survive. And everywhere we looked, the same quiet truth waited. Novikov's self-consistency principle permits the loop, but forbids the paradox. Echevarria, Klinkhammer and Thorne found a single setup blooming into an endless fan of consistent histories. Deutsch proved that a quantum state sent around the loop comes back as pure noise, every bit of new information scrubbed away. Hawking proposed his chronology protection to forbid the loops entirely, and then, with Cassidy in 1998, conceded he could not make the mechanism work. The Planck satellite searched the sky for Gödel's rotation and found, at odds of 121,000 to 1, that our universe does not spin. The closed time-like curve, it turns out, is not a doorway. It is a dead-end street, a path that goes somewhere only to return, on which nothing new can ever happen. That sterility is the whole lesson. A loop that can create no information and originate no history was offered as a way for existence to cause itself, to need no first cause, to ground itself in a circle. The physics itself refuses. The loop produces nothing and presupposes everything. Space-time already curved, matter already present, laws already in force. It cannot be the source of being because it is the clearest proof we have that geometry alone is a source of nothing. Something uncaused must stand behind it all, before space and time, powerful enough to be their origin, and, in selecting this reality out of all the configurations the mathematics allows, possessed of something only a mind possesses: will. The evidence, followed honestly, does not end in a self-made cosmos. It ends in an intelligent cause. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. We touched more than once on the principle that holds these loops consistent, the strange way the universe seems to forbid a paradox while permitting the path. But we only opened that door. If the question of how a fixed four-dimensional reality enforces its own consistency stayed with you, I have followed it much further, into the principle that does the enforcing. You will find where on the end screen now and in the description below. The equations of general relativity will let you draw a road back to your own beginning, and then, with the same patient mathematics, they will show you that the road creates nothing, carries nothing forward, and arrives exactly where it left. A dead-end street paved in space-time. The universe, it seems, keeps its streets safe for historians and keeps its deepest question, why there is anything here to loop at all, pointed somewhere beyond the loop. Good night.